Hi everyone, in this video, I'm going to go over the pre-lab questions and also the chemical equations that involve with the supplementary questions at the end as well. So this lab is going to involve with the buffer, which is going to be covered in chapter 15.2. All right, let's take a look at the pre-lab question number 2. Okay, so this problem asks us to calculate the pH of a buffer solution. Okay, so before we do the calculation, we need to understand first that the buffer solution is made of the conjugate acid and base. Okay, so and it can come in form of salt. Okay, so an example would be these two right here. Okay, so how do I know that these two are conjugate acid base pair? Remember, they are going to be different by one hydrogen atom, right? So in this case, which one would be conjugate acid and which one would be conjugate base? You will need to look at the number of hydrogen. Okay, so the one that have more hydrogen atom, right? So this is going to be an acid, right? And the one that have less hydrogen atom, this would be a base. Note that when we look at salt in chapter 14.8, we see the potassium ion, right? So this potassium ion right here come from the strong base. So therefore, this potassium ion is going to be pH neutral, which means it will not react with water. So therefore, if you're looking at in terms of the salt that we are going to use in the lab this week, we are going to only consider the counterpart of it, which is H2PO4 minus, and the other one would be HPO4 2 minus. Again, the reason for me excluding potassium is just because potassium will not do anything in the reaction. The only two components that will react in water would be these two conjugate acid-base pair. How can we calculate for a pH of a buffer solution then? Well, we are going to use the Henderson-Hasselbalch equation, which is written here. Note that this equation can only be used with the buffer solution. Okay, so pH of buffer will equal to pKa plus log of conjugate base divided by conjugate acid. Note that the p scale is the negative log scale. So therefore, if I want to know what is the pKa, all I have to do is take negative log of Ka, right? So we are given the Ka. So therefore, I'm just going to add the value of Ka in here. Okay, so the next thing we're going to take a look at is going to be the second part. Okay, so it's going to be that part right there. So this part right here, the conjugate acid and base have to be written in molar concentration. Okay, so it have to be the concentration. But because we're looking at a buffer solution and these two conjugate acid base pair are part of the buffer solution, they are going to have the same volume. So in this case, if you think about this, right, so if this is molarity, which is mole per liter, this is going to be mole per liter. You pretty much divide each of these mole, right, by the same volume. So therefore, this volume right here can cancel out. So therefore, what we can say is that we can actually use mole of the base, right, divide by mole of acid. You can just use that. The reason for that, because for buffer, the liter or the volume of both acid and base would be the same, right? So we can cancel those out. Now, before we plug this in, we first need to find out the mole first because the problem gives us in grams. So that means we need to convert from grams to mole. So to find out mole of each of these salt, all I have to do is just use the grams, right, and divide by its molar mass, and you're gonna get mole of potassium monohydrogen phosphate, and the other one would be use the grams of potassium dihydrogen phosphate, divide by its molar mass to get the mole of potassium dihydrogen phosphate. Okay, so now after you know mole, which one would be an acid, which one would be a base? We already talked about this, right? So the one that have less proton, this one would be a base. The one that have one more proton, this would be an acid. So therefore, you are going to plug this mole of the base here, and you're going to plug this mole of an acid right here. So again, you are welcome to find out the concentration. Again, if you want to find out concentration in molarity, all you have to do is just going to do 0.04994, right? Divide by liter. This is going to be 0.100 liter because you are going to convert that milliliter to liter. You are going to do the same thing here with molarity of the acid, right? So you're going to use mole of the acid divide by the liter of the volume, right? The liter volume of the solution. So you probably notice that the liter are the same. So therefore, in this case, even though you plug it in here, the liter will cancel each other out anyways, right? So you are going to end up obtaining the same answer. Okay, so what I'm going to do, I'm just going to leave it as mole because I know that the volume are the same. They're going to cancel each other out anyway. So I'm just going to add just the mole to just save my time. Okay, so if I do that, all you need to do next is just plug it in your calculator. You are going to get 7.17 as your result. So that means if you have this many grams of weak base, right, and this many grams of weak acid, right, so this is going to be the pH of this buffer solution. Again, as long as the solution has the same volume, right, we do not need to take the volume into account when we're looking at the concentration of this conjugate acid-base pair. Before we can answer the PreLab question number 3 and 4, we will need to understand first what does the buffer do. Okay, so a buffer solution can resist a large pH change when there is the small amount of the strong acid added to the solution, or a small amount of like strong base added to the solution. Okay, so I'm going to talk about the action in just a few minutes, but what does it mean? Okay, so it means that if a buffer solution has a pH of 8.65, when you add a small amount of strong acids such as HCl into the buffer solution, this is what is going to happen. Okay, so it's going to, this buffer right here is going to resist that pH change. So that means pH will change, but it will not change much. It's going to change slightly. So that means the choice that we can exclude would be A and B. It will not change that much, right? And also C as well. Okay, so now what would be the answer then between D and E? Okay, so this is going to be something that you will need to understand. Okay, so you add strong acid to a buffer. Yes, the buffer will resist the pH change, but this is an acid. So you're pretty much adding more of the proton concentration into the solution. So therefore, the pH will be slightly decreased, but because the solution become slightly more acidic. Okay, so the answer of this would be E. Okay, again, because you add acid to it. Now, what about if you have the same buffer solution, right, with the pH of 8.65? What happens if you add a small amount of strong base, such as sodium hydroxide? Okay, so again, you're adding a base. When you add a base, okay, so you are pretty much adding hydroxide ion. Okay, so what would that happen then? Well, again, buffer can resist a large pH change. So therefore, any of this pH change that is really large, right? In comparison to the pH of a buffer, you can actually eliminate those choices. So how much it would change then is depend on what you add. Since we add strong base is going to raise up the amount of hydroxide ion. So therefore, it's going to causing the pH of the buffer to slightly increase. So therefore, the answer of this would be D. Okay, so that's what you are going to observe in the lab as well. When you have a buffer solution, when you add acid, it's going to become slightly more acidic. If you add a base, it's going to become slightly more basic. Okay, but it will not change by much. Okay, what I'm going to talk about next is going to be related to the chemical equation that you are going to answer, which is going to be part of the supplementary question. Okay, so what would be the action of the buffer then? Like how buffer can resist a pH change? Okay, so this chemical equation will help you understand that. Okay, so when I'm going to talk about this case, so when we looking at a buffer solution, especially the one that we are going to do in lab, this buffer going to contain this salt right here, this two salt. Okay, so again, these two salt are conjugate acid-base pair, and we already established that this is going to be the acid part, but this is going to be the base part. Okay, so because a buffer solution contains both of these, so when you add something else to it, okay, so such as hydrochloric acid. Okay, so you are adding an acid to it, which is H+. Which one is going to neutralize that, right? Because the way that buffer can resist a pH change is going to be through the neutralization reaction. Okay, so in this case, if you think about this, right, we have hydrochloric acid. We have these two conjugate acid-base pair. You probably notice that the acid that is adding will not react with an acid, right? Because they both cannot cancel each other out. They cannot neutralize each other out. But the base that present within the buffer will be able to neutralize that adding acid. Okay, so therefore, in this case, when you add hydrochloric acid, you pretty much adding H+. Remember, this is strong acid. Strong acid will dissociate completely. Therefore, in the solution, there will be no longer molecule of hydrochloric acid. It will be only hydrogen ions, right? The proton and also chloride ion present. Okay, so in this case, I'm going to use the H+ because chloride ion will not do anything in the water. I'm going to react this added acid H plus to the base that we have, right? This is the base that we have. So I'm going to add that together. And again, because potassium will not do anything, so I'm going to ignore that potassium part. So the part that is going to react with the conjugate base HPO4 2 minus. Okay, so because this conjugate base can neutralize added acid, therefore it's going to resist, can resist the pH change or large pH change. So the final product will come out to be H2PO4 minus. You probably notice that, oh, this is the base. Oh, that's its conjugate acid. Oh, this conjugate acid also is going to be part of the acid here as well. So yes, so that's why in this case, right, because you are making more of the conjugate acid, therefore the pH of this solution would be slightly decreased. The reason for that is because this conjugate acid right here, again, can react with water, right? It can donate hydrogen to water to actually increase the hydrogen ion in the solution. So therefore, the pH will be slightly decreased. The reason why it doesn't decrease much is just because that this is a weak acid. It's only partially dissociated. Now, what about when the strong base added to the buffer, then what would happen? Well, when the strong base added to buffer, we know that the sodium part would be the pH neutral part, right? So the part that is going to give off is going to be the hydroxide, so OH minus. So this hydroxide ion will then react with the buffer, one of the component in the buffer solution. Okay, so we are going to react this hydroxide from sodium hydroxide. Which component that this hydroxide ion would react then? Well, this hydroxide ion would not react with the base, right? Base and base would not react with each other. But the base hydroxide would definitely react with an acid, right? Because base and acid will be able to neutralize each other. So in this case, you are going to get hydroxide ion to react with an acid, H2PO4 minus. The base hydroxide ion will accept proton from the weak acid, so it's going to yield water, and the other species would be the conjugate base, HPO4 2 minus. Okay, so again, because these two already neutralize each other, you are going to observe more and more of the conjugate base being produced. So since this is a base, so therefore, and also it's a weak base as well, so therefore it's going to increase the hydroxide ion in the solution slightly. So therefore the pH will slightly increase in this case. Here's a summary of what I just went over, right? So the buffer solution contain the weak acid and its conjugate base, right? So when you add these two together, you are going to form buffer solution. Because buffer solution contain both weak acid and its conjugate base, therefore it can actually resist a large pH change when acid and base is added. And the reason why the buffer can resist a pH change because it can undergo neutralization reaction with the added acid and base. For example, if you have a buffer solution that contain equal amount of weak acid and its conjugate base, okay, so when you add a strong acid, so let's say like you add 2 more of strong acid here, that 2 more of strong acid or the proton that come from a strong acid will then react with its conjugate base, right? So it's going to neutralize that. It's going to cause the concentration of the base to decrease, but it's also going to cause the concentration of weak acid to increase, right? Because it's going to yield weak acid. So as the concentration of weak acid increase, therefore in this case, you are going to end up with the pH slightly decreased, right? So that's how the pH of a buffer when you add acid slightly become lower because of that. Okay, so on the other hand, if you add a base, right? So let's say like 2 more of a base, the species that will react with a base would be a weak acid in this case. So therefore, the amount of weak acid will decrease, but you are going to generate more of the weak base, right? So as the concentration of weak base increase, you are going to end up with pH that is slightly higher than the original pH of the buffer.